So these are discrete, these are continuous. Okay. Now yn plus 1, by the same principle, gets replaced with y at tn plus 1, which is y at tn plus h. Yn minus 1 will be y at tn minus 1 step size, 1 y at tn minus h. And the idea is that if we make this substitution, a mechanical replacement of yn plus 1, yn minus 1, with the continuous image or pre-image from the differential equation, then this finite difference algorithm should generate on its own the ordinary differential equation. Let's see if it actually works. I've copied the algorithm over here. Yn plus 1 becomes y at tn. Tn plus h, already made a mistake. Yn becomes y at tn. H by 2, 3f. Now instead of yn, I have y at tn minus f. Y, instead of n minus 1, I have tn minus h. Tn minus h. In other words, we are applying our finite difference algorithm to the exact solution of some differential problem, and we are trying to figure out what this differential problem is. Now we expand in the Taylor series. On the left, y at tn plus h y prime. All quantities will be calculated at tn for the first derivative. I will also include the second derivative, just in case. The error term in the Taylor expression is h cubed. On the right, y at tn plus h over 2. We can't do anything with this term. It's just 3f of y at tn. And the next one requires some chain rule application. We expand y in the Taylor series, then we expand f in the Taylor series, so we get two expansions. I'll try to do it in one go. F at y at tn. Then by the chain rule, minus df by dy, dy by dt times the small quantity h. It comes with a minus, so it will be minus times minus plus h gf dy. I'm not going to write the arguments. It's the f dy computed at y at tn times dy by dt, which is y prime at tn. Also, because we have two variables in the function f, we need to expand in the Taylor series in the second variable as well. There is a minus h times minus in front gives us plus h, partial derivative df by dt computed at y at tn, and that's it, times 1, dt by dt. In this expansion, I'm making an error of order h squared, and let's stop for a minute and think, is this enough, or do I need to continue this expansion to higher orders? Probably not, because order h squared multiplied by h will be order h cubed is the same as the truncation error I made on the left. Right, anything we can do to simplify this formula? This is the beginning of the left-hand side. We can cross out y at t. This is already easy. Now, let us rearrange the terms a little bit. I'm going to drop the arguments tn, y at tn, tn, because we know where these derivatives are being calculated. So I have h y prime plus h squared over 2 y double prime plus a term of h cubed equals 3f minus f will be 2f divided by 2h times f. H squared over 2 h times h squared, h times h over squared, h squared over 2 df dy y prime plus df dt plus the error term order h squared times h order h cubed. Do we recognize a differential equation anywhere in here? Yes, we do, because at order h we have y prime equal to f. F is a function of y and t. That's the differential equation. Right, let's be precise. Our calculation shows is that to order h squared, our finite difference algorithm is consistent with the differential equation dy by dt equals f. But we can go one step further. Look at the h squared terms. And recognize the formula we've seen before. Y prime df dy. It's the full derivative d by dt of f of y of t. So at order h squared, our differential equation is still satisfied because what we have at order h squared is the derivative of the differential equation. Left-hand side is d by dt of y prime, right-hand side is d by dt of f. So the conclusion is that our finite difference algorithm approximates the differential equation or is consistent with the differential equation dy dt equal to f of yt to order h and order h squared. Therefore, it's consistent with a local truncation error of second order. We've proved the consistency and we've established that, and therefore the algorithm is consistent. With the equation dy dt equal f of yt, and it is consistent to second order. Right? Try to appreciate the difference in this verification of consistency as compared to what we were doing from the very beginning when we were deriving forward Euler, backward Euler, starting from the differential equation, its exact solution, then expanding the exact solution in a Taylor series, and then deriving the finite difference algorithm. That's the difference. That's what I wanted to say. And this kind of question is often asked in the exam you are shown some algorithm, and the question is it consistent with anything? What's the order of approximation if it is consistent? So this is a fairly standard question.